In this example problem, we're going to use the MomentArea Theorem to determine the following. We'll first find the initial camber of the beam, neglecting our self-weight, and then we'll find the total deflection under an applied load of 3.2 kips per foot. You can see we're using the same cross-section that we've been using in the examples throughout this module. To find the initial camber, the first thing that we'll need to do is find the moment-curvature relationship for this section. You can see here the moment-curvature relationship that we found earlier using response 2000. Note that in this portion, I'm neglecting self-weight just so that we have a kind of the simplest case with a constant moment along the length of the beam. Our next step is to determine the moment and curvature along the length of the beam. Because we're neglecting self-weight, the applied moment along the length of the beam is going to be equal to 0. We take into account the effects of our eccentric pre-stressing in our moment curvature diagram. So we don't need to add those effects into our moment diagram. So then, with our moment equal to 0 along the length, we can find the corresponding curvature to 0 moment from our moment curvature diagram, and we'll find that curvature to be negative 10.43 times 10 to the negative 6th. We know because we have a constant moment and we have the same moment curvature diagram along the length because we have the same strand profile and same cross-section shape that we'll have a constant curvature diagram along the length as shown here. At this point, we need to now calculate our deflection using our curvature along the length and our MomentArea theorem. For a simply supported beam, we can find our deflection at midspan using a couple different points as shown here. We'll need to find our theta A, we'll need to find our tangent, or I guess the distance between the tangent coming from A at point C and at point B. And we can use those to find our deflection. By our deflection being equal to theta A times L over 2, which will give us that point there, minus T C over A, which would take us back up here to give us that deflection there. So on the next couple slides, we'll find this deflection. We can use the curvature diagram with our different variables to find our deflection. We'll start by finding T sub B over A. To find this, we need the area of the curvature diagram between B and A times the distance between the center of this area and point B. You can see our area is theta 1 times L, and our distance component is going to be L over 2. We can find the theta A then by taking this T sub B over A divided by our length. And if we simplify that, we'll get the value being phi 1 times L over 2. Note that with MomentArea theorem, we also know that the change in slope between 2 points is equal to the area of that of the curvature diagram. So we can also find our theta A by finding the area of the curvature diagram between a point of 0 slope, which we know is at midspan here, and the point where we're interested in the rotation, which is at point A here. So finding that area, we would have L over 2 times phi sub 1, which would be phi sub 1 L over 2. So you can see the areas are equal. Next, we need to find T sub C over A. To find T sub C over A, we need to take the area of the curvature diagram between A and C, times which is phi sub 1 times L over 2, times the distance between C and the center of this area, L over 4. So we'll get that value then to be phi sub 1 L squared over 8. We can then find our deflection by taking theta A times L over 2, which brings us to this point, minus T sub C over A, and that would give us our final deflection. So simplifying here, we can find that the deflection is going to be equal to our curvature times L squared over 8. And if we plug in our values, our known curvature and our known beam length, then we can find our deflection would be an upward deflection of 0.075 inches. And this is our initial camber caused by our pre-stressing, not including the self-weight of the beam. The next part of the problem is we want to find the total deflection using the MomentArea Theorem with our given distributed load. The first step is again to find the moment curvature relationship for the section. And this is the same moment curvature relationship. And again, we found this using response 2000 in a previous example. Next, we need to determine the moment along the length of the beam, and then we'll use that moment with our curvature diagram to find the curvature along the length of the beam. You can see the moment here, just with our applied distributed load of 3.2 kips per foot. We have our moment here with 0 moment at the ends and max moment at midspan. We can then use our curvature or our moment curvature diagram to find the curvature along the length. And note that these moments will not always correspond with an exact point on our moment curvature diagram. So I'll just use a linear interpolation if we have a moment between 2 points on our diagram. So you can see the equation that I'll use for linear interpolation here. Using this procedure, we can find our curvature along the length of the beam. So you can see here the curvature diagram along the length of the beam under the applied load, 3.2 kips per foot. Now, next we need to find the average curvature of each segment. So we have our curvature diagram discretized, and we're going to find the average curvature within each one of these discretizations. You can see we just find the average curvature in one of these segments by taking the curvature at one end plus the curvature at the other divided by 2. And we can do that along the length to get this discretized curvature diagram. We can then use our MomentArea Theorem to determine the deflection at midspan from the distributed load using the discretized curvature diagram from the previous slide. Just like the first part of the example, our total deflection will be equal to our theta A times L over 2 minus T sub C over A, and that'll give us our deflection delta C. So we can find those two values just like we did in the previous part of this problem. We'll need to use the summation of the contribution of each one of these segments to find our T sub B over A and T sub C over A. So our area of the segment is going to be the width of the segment times the average curvature in that segment, and the distance component for the segment is going to be between the center of the segment and point B or C, depending on if we're looking for T sub B over A or T sub C over A. So we're going to use these two summations to find our T sub B over A and T sub C over A, and then we can use these to calculate our deflection. Shown on this slide is a copy of a spreadsheet that I developed to complete all these summations from the previous slide. You can see that I find the moment and curvature at a number of different points along the length, and then I break up my curvature diagram into 20 different segments. For each one of these segments, I need to find the average curvature, the width of the segment, which I keep a consistent 12 inches, and then the distance between point B and the center of the segment and point C and the center of the segment. So you can see then we can find the average curvature times the width of the segment times the distance component for each one of the segments. For our T sub B over A, we need to sum up all the values from these different segments between points A and B, which is the entire length of the beam. For our T sub C over A, we need to just sum the segments between point A and C, which in this case is only half the beam. So you can see here our T sub B over A is going to be 1.695 inches, and our t sub c over a is going to be 0.174 inches. Using these values, we can then find our theta a, which is our t sub b over a divided by L, which will give us a rotation here of 0.00706 radians. And then we can find our total deflection just using the equation from a couple slides ago, our rotation times L over 2 minus t sub c over a, which gives us our deflection of 0.673 inches. So this is our final answer for this problem. Note that for simply supported beams with symmetric loading, we can make a simplification. And what we can do is we know that there's 0 rotation at midspan, so at our point C. So our tangent extending from C out to A, T sub A over C is going to be equal to our deflection delta C. So in this case, we could also find our deflection by summing all of our segment contributions, but this time having a distance between point A and the center of the segment, and sum all the segment contributions between point A and point C. And if you do this, you'll get the same answer as we found doing the more general approach. So that concludes this example problem.